The stresses involved in the metal forming are the compressive, tensile stresses, tensile and compressive, and the shear stresses. Material with lower yield strength and higher ductility are easier to be formed. The metal ductility increases and the yield strength decreases by increasing the metal temperatures. Other factors like the strain rate and the friction are also affecting the metal forming process. The bulk deformation processes can be classified into the bulk deformation and the shield metal working. In the bulk deformation processes, work parts with relatively low surface area to volume ratios, like simple geometries of the cylindrical pellets or the rectangular bars. Usually it's going to have a significant deformation and massive changes in the shape. Examples for that are the rolling, the forging, the extrusion, and the wire and the bar drawings. In the sheet metal working, the geometries with high surface area to volume ratio like the metal sheet, strips, and the coils. The process of the forming, like the bending, cutting, and extra, is called the sheet metal working or the press working because these operations are performed on the presses. Parts are going to be called the stamping, and the usual tooling is going to be the punch and the die. The main examples for the sheet metal working are the bending and the TV drawing and the shearing process. In the elastic region, the material behavior follows the Hooke's law. After the yield point, the plastic region will start. The plastic region of the stress-strain curve is the primary interest because the material will be plastically deformed in this region. In the plastic region, the metal behavior is expressed by the flow curve. The flow curve based on the true stress and strain. The average flow stress in relation to the flow stress and the strength. For most of the metals, at the room temperature, the strength increases when deformed due to the strain hardening. The flow stress is the stress that must be applied to cause the material to be deformed at constant strain rate in its plastic region. Thus, the flow stress is yield strength as a function of strain. The forming process requires force to be accomplished, and this force is proportional to the flow stress. As the metal temperature will increase, the K and the N value will be decreased. Thus, at higher temperature, a lower stress value and higher ductility will be resulted. Accordingly, a low force and power to accomplish the deformation operation at elevated temperature will be required. The metal forming can be classified to the cold working that performed at the room temperature or slightly above. Many of the cold forming processes are important mass production operations. These operations are net shape or near net shape processes. The warm working performed at a temperature above the room temperature but below the recrystallization temperature. The dividing line between the cold working and the warm working often expressed in terms of the melting points, while the temperature required for the warm working is around 30% of the melting points of that metal. The hot working is performed at a temperature above the crystallization temperature. The crystallization temperature is around 50% of the melting point. The metal will continue to soften as the temperature increases above the 50% of the melting points, and this will enhancing the advantage of the hot working above this level. The isothermal forming refers to the forming operations that are going to be carried out in such way to eliminate the surface cooling and the results of the thermal gradients of the work parts. It's accomplished by preheating the tools that come into contact with the work part to the same temperature of that work metal. This weakens the tool and reduces the tool life, but it avoids the problem related to the other forming processes. The eliminating of the heating in the cold working resulting in many properties. First, the accuracy, the tolerances, the better surface finishing, the strength and the hardness due to strain hardening. Also, the grain flow during the deformation can cause undesirable directional properties in that product. Finally, as no heating of the work required, the product is going to be faster and also is considered to be a green technology. In the warm working, lower force and power than the cold working are required. Also, more intricate work geometries are going to be possible. As the process required to do some heating and cooling, so the need for the annealing may be reduced or eliminated. In the hot working, the work part shape can be significantly altered with lower forces and power requirements. The metals that usually fracture in the cold working can be hot formed. Strength properties of the products are generally isotropic. Finally, no strengthening of the part occurs from the work hardening. Strain rate is the change in strain of the material with respect to time. Theoretically, a metal in hot working behaves like a perfectly plastic material, where the strain hardening exponent is equal to zero. The metal should continue to flow in the same flow stresses once the stress is going to be reached. This flow stress is a function of the temperature. At hot working temperature, the flow stress also depends on the strain rate. As strain rate increases, the resistance to deformation will increase. This effect is known as the strain rate sensitivity. We have already observed that the flow stress of the metal is a function of the temperature. At the temperature of the hot working, the flow stress will depend on the strain rate. The effect of the strain rate on the strength property is known as strain rate sensitivity. The effect can be seen in the figure. As strain rate increases, the resistance to deformation will increase. Usually, the plots approximately as a straight line of the log-log graph and thus leading to the relationship of the YF. The C is strength constant, which is similar but not equal to the strength coefficient in the flow curve equation. And the M is strain rate sensitivity exponent. The constant C indicated by the intersection of each plot with the vertical dashed line at the strain rate equal to 1 will decreases, and the M, which is the slope of each plot, will increases with the increasing of the temperature. The observations about the strain rate sensitivity that the increasing the temperature will decrease the C and increase the M. At room temperature, the effects of the strain rate is almost negligible. The flow curve alone is a good representation of the material behavior.